Hello and welcome back to Calculus 3. This is the second part of 13.5 lines and planes in space. We are going to review quickly the equation of the line, which is given by this parametric set, which can be written in a vector form, or it can be written as the parametric set on the bottom. These three equations have to be given together. All three equations at the same time represent the line. And there is another form which I did not mention earlier. And that form is, if you solve each one of these equations for t, and you equal them all, you come up with this three-sided equation of the line. So there will be a third way to present the line. And you might run into a problem where the line is given that way, so you need to know that form as well if you run into it. So if you have x equals x0 plus at, y equals y0 plus bt, and z equals z0 plus ct, you can solve for t as x minus x0 over a. You can solve for t as y minus y0 over b. And you can solve at t equals z minus z0 over c. And now when you set all t's equal to each other, you get x minus x0 over a equals y minus y0 over b equals z minus z0 over c. And that's also a form of line in 3D. So that will be the third equation. Now, what we did yesterday, we found equation of the line given 2 points. We know that if you have 2 points, you can find the equation of the line. So we used our 2 points to calculate vector v, and then we had v times t, and then we used the p0 as the anchor, and that was that one. And then the line segment is the finite line. So the difference between the two lines is that the previous example was infinities, right? And the now finite line has the beginning and the end, and those were the endpoints that were given in the problem. Now, a few more things that we can compute. One of them would be distance between a point and a line. Distance between the point and the line. And that one is the distance d, given as the, well, let me first write. So we're talking about the distance between the point and the line. So point Q in space and point P on the line. And the line is given by r equals r0 plus tv, right? That's our vector notation for the line. The same like y equals mx plus b. So the distance is given by d equals, so this is the formula. We have the magnitude of v cross vector pq divided by magnitude of v.
V is still a vector.
Yes, V is the vector that describes the line. So you have your line L, and you have a point Q somewhere in space. Now, the closest distance on the flat surface, the closest distance is the straight line. And that straight line has to be perpendicular to the line L in order for it, right? If you have anything else that it's not perpendicular, you see it's longer, right? That should be. Now, that only works on the flat space. It doesn't work on a curved space. You know that all of the airplanes have as they fly from between continents, they follow geodesic. They follow the curved path because that would be shortest distance on the surface of the planet, which is round. I know, shocking for someone, but it's round. And this is your distance D that we are looking for. So here you see that angle of 90 degrees, which is why we have a cross product. And the vector V is any vector that is in the direction of, so vector V is any vector that is in direction of our line. See, dividing vector V with its magnitude, it's giving us the unit vector, right? So technically you are crossing the unit vector to find the perpendicular vector, right? You're crossing the PQ. Oh, point P. All right, so then obviously you just plug stuff in and you're done. It's not a big deal. Is there anything else that it's cool that we can calculate? I almost forgot the intersection point between the, great. So let's talk about the lines. Parallel, perpendicular, or skew. So two lines can be parallel, perpendicular, or they can miss each other in space. This is all in 3D. So you have more than one way for the lines not to intersect in 3D. In 2D, the only way to have lines not intersecting is to be parallel in 2D. But in 3D, right, you can have one line going like this and another line going like that. Right? They don't intersect. So, and they are at the angle. So more options for two-dimensional lines to intersect or not intersect in 3D space. Parallel lines have vector V, same vector V, because that's your slope. Vector V is your 3D slope. Vector V gives you the direction of that line in space. So, same V. Over here, line 1 and line 2, you will have V1 and V2. The dot product is 0. That should be common sense from last time, because two vectors are perpendicular, orthogonal, if their dot product is 0. So two lines intersect at the 90 degrees if their vectors v have the dot product of 0. And if both of these conditions fail, then you have the skew line, which means they do not intersect, and they're not parallel, they're not perpendicular. It's just there's nothing in common. So they ask you to consider two lines in space. Problem 34. X equals 4 plus 5t, y equals negative 2t, z equals 1 plus 3t, and the second line, x equals 10s, y equals 6 plus 4s, and z equals 4 plus 6x. 6s.
What's the z?
4 plus 6s. Determine whether the following pairs of lines are parallel, intersect at a single point, or are skew. If the lines are parallel, determine whether they are the same line and thus intersect at all points. If the lines intersect at a single point, determine the point of intersection. Great. What now?
Determine the v of each of them. From there we can say...
Excellent. So, what's V1? Yes. What are the A, B, and C for the V1?
Negative 5,
Yes. 5, negative 2, and 3. Excellent. So those are the values in front of t's. That's like your slope, right? Remember, y equal mx plus b. Here's your mx plus b. So m is your third dimensional slope is now v. And what's v2? 10, 4, and 6. So if you look at these two lines, you can, are they parallel? Are they scalar multiples of each other? No, right? Because of the negative 2. If there was a positive 2, it would be a different story. Let me just verify that. Yeah, it's negative 2. If this was a positive 2, then these two vectors would be scalar multiples of each other. They would be the same direction, and then these lines would be parallel. But because this is a negative 2, they are not parallel, because they are not multiples of each other. Maybe I should say same v's, or v1 is equal to some constant k times v2, right? Scalar multiple, because if I have a vector with a magnitude of half and a vector of magnitude of 1, they're still having the same direction, right? It's the same vector times the scaling factor. So carrier vectors v1 and v2. So v1 equal kv2, the way I just defined it up there, fails. So not parallel, right? Let's take a look at the dot product. What's v1 dot v2? Is it a 0? No. We have 50 minus 8 plus 18, that's 60, so cross product 60 different than 0, not parallel, not orthogonal. Now, do they intersect? The question is there a point in space where they share x, y, and z to be the same. Does that make sense? If you are intersecting two objects in space, they have to have the same coordinates because they need to be in the same location, right? So if these two lines are to meet anywhere in the infinity of space, they must have the same x, y, and z. So this is why you get to set these equations equal to each other. X equals x, y equals y, z equals z. And then see if it's possible to solve the system. 4 plus 5t is equal to 10s. Negative 2t is equal to 6 plus 4s. And 1 plus 3t is equal to 4 plus 6s. So this is our system. Now you are going to use two equations to come up with a t and s, and that t and s will either work or not work in the third equation. So that's when the deal gets broke. How many equations? Here we have our linear algebra expert right here. And linear algebra expert here will tell you that for overdetermined system, that means you have more equations than variables, you can still have the solution as long as those two solutions satisfy the third equation. So we are going to use the first two equations to solve this. You can use any two equations that you pick to solve the system to get t equals a number, s equals a number. Now, what kind of witchcraft you are going to use to solve the system, that's up to you. You have matrices, you have substitution, you have elimination, essential oils, whatever. Whatever works. Now, when you get t and s, there will be numbers. And you plug those in the third equation, the one you haven't used yet, and if it works in that equation, then they intersect. Because you just found t and s that are possible to be used for x and y and z of both of these lines to have a common point. If they do not satisfy the third equation, that means that those t and s would actually not meet. See, you found the t and s so that x and y equations align, but then the z equation doesn't align, so it would just be askew and they don't meet at all. Now, to solve the system from the upper two equations, we have 5t minus 10s is equal to negative 4, and you have negative 2t minus 4s is equal to 6. And now you solve this any way you know. I'm going to leave the 5t minus 10s equals to negative 4 and divide the bottom equation by 2 because I can simplify that into negative t minus 2s is equal to 3.
Can you simplify the top one? Oh, wait, you end up with a fraction.
Yeah, it's a 4 over there. So I'm going to multiply bottom by 5. 5t minus 10s is equal to negative 4. Negative 5t plus 10s is equal to 15. All of these cancel. Did I do this right?
I just don't understand.
No, I copied something somewhere wrong, right? Positive, negative, 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 positive, negative, 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 positive, negative. Ah, that's a minus. There we go. So these die. It's negative 20. S equals 11. S equals negative 11. Really? Negative 11 over 20. Yeah, kill me now, right? So now that we have S, we can go back into any of the equations and calculate our t. So from this equation here, I have that t is equal to negative 3 minus 2 times, and s is negative 11 over 20. Holy nightmare, really? T equals negative 3 plus 11 over 10. So this is negative 30, negative 19 over 10. Amazing. Now we're going to bring in that third equation. 1 plus 3, and t is negative 19 over 10. And that should be the same as 4 plus 6 times negative 11 over 20. One plus 3 times that's negative 57 over 10 is equal to 4 plus, now this will cancel to 10, and this is still going to be 3, so negative 33 over 10. This is 10 over 10, so negative 47 over 10. And this is 40 minus 33 over 10. That's equal to 7 over 10. So they don't, it doesn't work. It doesn't work on the third equation, so it fails there, and we have skew because they do not intersect. So we showed that they're not parallel because V1 was not a constant multiple or the, yes?
Does what you just did there cover whether they intersect generally or if they intersect at the same time?
Generally, because I equated x value to x value, z value to z, right? So I equated the equations because one is expressed in a parameter t, the other one is parameter s, and they move, one can move in time, the other one can move in space, whatever, right? Good. I see these really cute problems over here. So how about you you solve one of these? I really like, wow. All right, try one of these and then I promise, then we'll do new stuff. This is too cool to pass on. Problem 20 says find the line, find the equation of the line, find the equation of the line passing through point negative 3, 4, 2, that it's perpendicular to both vector u given as 1, 1, negative 5 and vector v 0, 4, 0. It's gonna be awesome. Does anyone have any ideas of how we should proceed to this? You are given the condition that your line has to be perpendicular to two vectors, orthogonal to two vectors at the same time.
The cross product?
Cross product of what? Between what?
Of you and me to get a vector that is perpendicular and then have that vector pass through that point.
Excellent. So, and I have to show you one more time with these vectors, the markers. All right, so black marker is vector u, blue marker is vector v, and they are any vectors that are floating in space, right? If you do the cross product of those two vectors, the vector that you get is going to be orthogonal to those vectors, meaning perpendicular. So if you look on the side, there is a 90 degrees to the blue and 90 degrees to black. So cross product between vectors u and v will give you the vector v, which is the direction of the vector that you want, and then you just shoot that vector through your -3, 4, 2, which is your x0, y0, z0. So all we need to do is that cross product. U cross V is ijk 1, 1, and -5, 0, 4, 0. When you do the cross product, for I, we have 1 times 0 plus 20. For J, we have 0, 0, 0. And for K, we have 4 minus 0. So the cross product will give us 20, 0, and 4. I'm just going to say work goes here. And then I'll put this, you know what this symbol is, right? Just do it, exactly. So now I have that my direction vector v, oh, this is terrible. You know what? I'm going to change this into vector w. So that way you don't have to erase anything. Because remember, our vector for the line is v and then multiplied by t. So this is your vector v, 20, 0, and 4. And now to set your line, you have your x equals y equals z equal. The point given to you is -3, 4, 2. And then you have plus 20t plus 0 and plus 4t. That's the parametric equation. What happened? They asked for the equation of the line. I got it. I'm done.
And that intersects through -3, 4.
Yes, that's the, I use that as a, right?
Yeah.
That's my anchor point for the line, because it goes through that point. That's the fixed point. Great. So what you have seen there is the solution for this problem 20. And now we are going to take care of the second half of the lecture, which is dealing with equations of planes. you all know what the plane is. It's the flat surface of your desk, it's the flat surface of the screen, it's the flat surface of the board, it's the floor, it's the ceiling. Plane is just this flat surface. So you know the concept of it, but we do have mathematical definition that sounds nothing like that. So let's write that, because why simply if we can complicate things. Definition for plane in 3D space. Given a fixed point P0, and a non-zero normal vector n, that's the one you're going to get from cross product, and a non-zero normal vector n with the arrow, the set of point P, the set of points P in R3, this is the 3D, for which P0P is orthogonal to n, is called a plane. Okay, so this begs for a terrible picture. Here I have a vector n and a plane lowercase p. And this is where point P0 is, which has coordinates x0, y0, z0. This plane is the set of all points containing a point P, which has coordinates x, y, z. So what is point P? Point P is all of the points. All of these points that you can possibly put anywhere. Each one of these is a point P, one at a time. So you pick a point P somewhere and you stretch a P0 P vector. There is a 90 degrees there. You pick a different point P, fine, right there. Stretch a vector, there is a 90 degree angle. So no matter where you pick point P, when you stretch P0 P vector, there is going to be 90 degrees between the red and the black vector. Point P has x, y, z coordinates because point P is supposed to assume every location on this infinite plane. And this plane goes in all of these directions forever. So, if I have this black marker here is the normal vector on this desk that I already told you earlier that the normal vector is enough to describe the entire plane because normal vector is always perpendicular to the plane. If the plane tilts, the normal vector is now different, right? And then remember that the normal plane was the cross product. Normal vector was the cross product, so you get either going up or going down depending which vector you pick. But it doesn't matter which vector you use, the one on the top or one on the bottom, it's the same. We'll see why shortly. So now, if I have a plane, like a surface on my desk, then every point on the surface of this desk is a point P that you can connect to the bottom of the vector n, and all of those points, which is now represented by the blue marker as I go around, all of those points are always 90 degrees, as you can see. They're always 90 degrees to the black markers, which are my normal vectors. Even if the plane is tilted to any, right, as soon as I put point P, which is the tip of the blue marker and the black marker are always at 90 degrees. So definition does make sense, but at no point it tells you it's just a flat surface. Right? So now our normal vector n is going to have a, b, c. That's just like your vector v. Vector v is the third-dimensional slope for the line. Now vector n is acting like a third-dimensional slope orientation for the plane. So that's going to be your ABC vector. And if you think about this for about 17 seconds, it says that vector n and vector POP are orthogonal. Now, what do we know about the dot product for orthogonal vectors? Equal to 0. So n dotted with POP is equal to 0. Now let's write this out. Vector n is given by ABC dotted with, and the vector POP, remember we are supposed to subtract coordinates, right? So x coordinate is x minus x0, y coordinate is y minus y0, and z coordinate is z minus z0 equal to 0. We know that we are supposed to multiply first component with first component, then add b times y and add c times z. So we get a times x minus x0 plus b y minus y0 plus c z minus z0 equals to 0. Ta-da! This is what we were after. That's the equation of the plane. Hope you're not disappointed. Equation of the plane. Now x0, y0, z0 are numbers. A, b, and c are numbers. So we can actually, before I go there, please note that, remember what I said, you get your normal vector by the cross product of the two vectors in a plane. And cross product is not commutative. Great. If you do cross product one way, you get the normal vector pointing, let's say, up. If you swap the vectors and do cross product the other way, you get that normal vector pointing down. That was discovered and talked about yesterday. Now, it doesn't matter if you are using the normal vector pointing up or pointing down. Look at the equation. It's equal to 0. If I switch all of the signs for A, B, and C, that's equivalent to multiplying both sides of the equations by -1. You see that the right-hand side of the equation technically doesn't change at all, because it's 0. So it doesn't matter which way you cross your vectors to get the equation of the plane. We can simplify this a little bit by distributing A and B and C, and then using AX0, BY0, and CZ0, those are all numbers. Kick that to the right side and call it all a D. So if I distribute A, B, C, I will get AX plus BY plus CZ equal to AX0 plus BY0 plus CZ0. And I'm going to call all of this constant D because that's all numbers, and get to this more compact value, more compact equation for equation of the line, where this D is given as, it's fine. So this is also equation of the plane, and you know that your D is all of this stuff. Call that the D. The most basic problem that you can find
Holy.
well, thank you, now I feel much better. The most basic problem for this that you can pretty much bet to see on one of the exams, quizzes, or final is to find the equation of the plane given 3 points. Should be common sense that if you have 3 points in space, they are bare minimum to define a plane. I already did this yesterday. 2 points, not good because it's wobbly. 1 point, not good, it's wobbly. So 3 is the smallest amount of points, right? Can you have 4? Sure. 5? Yes, right? This is the way you hold the tray, right? There's another one. No, whatever. So find equation of the plane given 3 points. As I said, this problem has to show up either exam 1, final, quizzes online that we do. This must be somewhere. Whatever points, it doesn't matter. 5, -1, 3, next point 2, 2, 0, and the last point is 6, 6, 6. There we go. Very original. What would be your plan of attack here? What should you do first?
Go ahead, just say it.
Create 2 vectors off of those, and then cross product, take the cross product to the fundamental vector.
Excellent. We first need those blue and black markers, right, which are the vectors in the plane. So use a set of points. Now make sure that you have 1 point as your anchor. So pick a point that is going to be the emergent point for your vectors. One of the 3 points has to be your anchor point. Now it would be cool if you guys pick different points for the anchor, because you all have to get the same answer. If I pick the first point to be my anchor point, then I have vector from here to here, which means I'm subtracting this way, and vector from here to there, which means I'm subtracting this way. And then this point is going to be your x0, y0, z0. You can't just pick anything, right? Whatever you pick to be your anchor points for the vectors to create vectors, that anchor point is your x0, y0 for the equation of the line that is the part of this D. Clearly you will be using the upper equation better than this one. This is just, just show equation. You use the upper one. So pick whatever you want to be your anchor point. And then when you compute everything, everyone's answer has to be the same. At the end, because it's the same plane for everyone. So I'm just gonna do this by anchoring 666. If you probably anchored 5, negative 1, 3. So we should all get the same answer at the end. Did anyone anchor 2, 2, 0? Oh, great. So we'll have a good variety. Okay. So, is this what you guys have? Well, you have to have 30x and 6y, right?
Yeah, I didn't get that. I could have messed up another.
Well, I could have messed it up too, but... So if I fix a point, then all the other coordinates minus that point. So 5 would be a terminal. 5 minus 6 is negative 1. Negative 1 minus 6 is negative 7. 3 minus 6 is negative 3. 2 minus 6 is negative 4. 2 minus 6 is negative 4. 0 minus 6 is negative 6. Now, when I kill i's, 7 times 2, 42. 42 minus 12 is 30. When I kill j's, it's 6 minus 12 is negative 6, but then a negative for j is positive 6. And then 24 is going to be, you kill k's, that's 4 minus 28. 4 minus 28 is negative 24. And since I anchored 6, 6, 6, then I have those as x0, y0, z0, and I place them in the parentheses. And now, this is where our equations need to be the same. When I go 30x plus 6y minus 24z is equal to 30 times 6 plus 36 minus 24 times 6. And then we will see that they can be canceled, right? So 30x plus 6y minus 24z is equal to, oh, this is actually, hold on, I'm going to write this as 6 times 6 times 6. I can factor out 6. And then that's 12, so 72, right? Because if I factor out 6, 30, 36 minus 24 is 12, 72, good. So now, observe that I can cancel by 6 everywhere. So when I cancel by 6, 30 divided by 6 is 5x, plus y, minus 4z is equal to 12.
Your n vector, I think, is supposed to be
negative 30. So if I kill i's, then I have negative 7 times negative 6, which is positive 42, minus negative 4 times negative 3 is positive 12, and that's positive 30, and then I is positive, only j is negative, so it's positive 30. Well, that should be good.
Go back to the original points.
Original points. Oh.
Yeah.
5, negative 1, 3. Now all of this stuff is just computationally very intensive. You sit and you grind. This problem would be great if you guys took this, during the homework practice, and just take this problem or come up with your own points, it doesn't matter, and then do the problem 3 ways, anchoring different point, keep calculating until, and simplifying and canceling until you get all of them to be the same at the end. Because it doesn't really matter which one of the 3 points you anchor. Right? If I am working on this board and I have 3 points in space, it doesn't matter which one is going to produce my n vector, right? So I can have them, if I anchor this one, then my vectors u and v in the plane, and my n would be there, right? So, but it's important that whatever you anchor, that's the one that is your fixed point, which is your x0, y0, z0 for that d calculation. That's important. You are allowed to pick any. If you don't like this configuration, fine. Pick whatever else you want it to be. So you just get rid of all of this, and then you say, I'm going to anchor this point here to be my x0, y0, z0, which means then your vectors are going to emerge from there, and your n vector will be here. So whatever you anchor, that's the one that you place in. And when you simplify all the way at the end, this equation needs to be the same no matter which point you anchored, because it's the same plane. It's a question who made an algebra or arithmetic mistake, me or you.
Oh,
be surprised. I don't do numbers. You know, I keep purposely making mistakes to just see if you're paying attention. You know, that's the. I keep checking and testing, you know, all these ideas. So now we have equation of the plane. We know to get the normal vector. Great. How do we know if the planes are parallel or orthogonal?
We do those tests on normal vectors.
Nice. Each plane is completely described by its normal vector. So, if the normal vectors are having the same v, then they are parallel planes. If the dot product of the normal vectors is 0, the planes are perpendicular. Actually, I could use your help. So here is the experiment. Can you please hold that perpendicular? Or you have to stand here so people can see. All right. Look at that. Normal vector on the table, normal vector on the keyboard, and then they are normal as well. Right? So if I dot the normal vectors and I get that dot product to be 0, that means that the plane and the surface, the other plane, both are also orthogonal, perpendicular, right? So parallel planes have normal vector 1 to be a constant multiple of the normal vector 2. Orthogonal planes have normal vector 1 dotted with the normal vector 2 to equal to 0. Now, if the two planes are intersecting, what do you get when the two planes intersect? Thank you. You get a line. Look at the line between in the corner, right? That's the one that it's annoying to paint. So, I mean, if you have the accent wall, right? So, when two planes intersect, you get a line. Great. I want to know what's the equation of that line. I'll give you two planes. You figure out that equation. That's a possible problem for a test, right? Another one is, sure that the ceiling and the wall are intersecting at 90 degrees, right? Sure. But how would I find if the two planes are not intersecting at 90 degrees? Look at the design of my tablet over here. That's not 90 degrees. There's a plane for this back over here, and there is this tablet. So how do I find this angle?
The normal vectors.
Yes, the dot product cosine formula of the normal vectors. It's the same. That's the basic geometry. Great. So I'm going to give you just a random problem. Let's go with 67. 3x plus 2y minus 3z is equal to 10. That's your plane 1. P1. Plane 2. Negative 6x, negative 10y, plus z equals to 10. Parallel, orthogonal, neither. So this is fairly quick problem, right? All we need to do is to fish out n1, which is clearly given, 3, 2, negative 3. That's your ABC, right? And then fish out n2 from the second one, negative 6, negative 10, 1. And then, are there constant multiples of each other? No. n1 is not k n2. So no parallel. N1 dot n2, we are looking now for the cross product, from the dot product to be 0. So what I have is negative 18, negative 20, and negative, so they're all negative. So not 0. I don't even care what this is. Actually, we do need it because we are going to do the angle to see at which angle they calculate. So this is negative 41. So that's the dot product. So now that means not orthogonal. And now finally, to find the theta, we have inverse cosine of our negative 41 divided by square root of 3 squared plus 2 squared plus 3 squared. Don't worry about negatives, square will kill them. Times the square root of 6 squared plus 10 squared plus 1 squared. Theta equals inverse cosine of negative 41 divided by square root of 9, 18, 22 times 137. Make sure your calculator is in degrees. Inverse cosine. I am not going to forget the square root like I did last time. I have 138 degrees, 0.3. So 138.3. Great. That's it. Let's take a break and then we'll look at quadratic surfaces.